Welcome to The Explainer. Today we're diving into one of the most fascinating yet completely invisible sequences in all of modern tech. We're talking about that wild, layered sequence that happens in those fleeting moments between you hitting the power button and actually seeing your desktop appear. It is literally a relay race happening right under your fingertips. Seriously, what actually happens in the dark before your screen lights up? We kind of take it for granted, right? You press a button, boom, the computer's on. But it's actually this hidden chain reaction of steadily increasing capability. Each layer of your system wakes up, knocks out a highly specific task, and then passes the baton to a slightly smarter, more capable layer.
Okay, let's just quickly map this out. 1. Waking the hardware up. 2. Passing the baton. 3. The kernel takes charge. 4. The power of PID1. And 5. The final handoff.
All right, stage 1, waking the hardware up. So before your OS can do, well, anything at all, the first runner in our relay has to hit the track. And that's your motherboard's firmware. The very first code that executes isn't sitting on your SSD. It's hardwired into a tiny firmware chip right on the motherboard. Because your CPU is hardwired to look at a fixed memory address for its very first instruction, it points straight to this chip, which means this firmware exists totally independent of the operating system. You could literally rip your storage drive out, and this code would still run.
Now, you've definitely heard of BIOS. That legacy BIOS is a relic from the 1980s. Super limited, runs in a restricted processor mode, and caps out at booting from 2 terabyte drives with that old MBR partition scheme. But modern rigs use UEFI, which is a massive upgrade. We're talking support for giant drives with GPT partitioning, its own mini file system, and crucially, secure boot. Secure boot is absolutely essential these days because it meticulously verifies that the code it's about to load hasn't been tampered with.
But before the firmware does any of that, it runs a post, the power on self-test. It's basically a rapid-fire hardware sanity check. CPU responding? Yep. RAM present and working? Yep. Keyboard plugged in? You get the idea. We've all experienced that sheer, heart-dropping terror of a black screen and those angry beep codes when a post fails. But hey, fun fact, if it crashes right here, your operating system is totally innocent. It hasn't even been loaded yet.
Moving on to stage 2, passing the baton. So the firmware has confirmed the hardware has a pulse, but it's way too limited to run a full OS. It's got a handoff control. It checks your boot order, maybe your SSD, maybe a USB, looking for a small piece of code that can load the heavy hitters. Enter the bootloader. If you're on Linux, this is probably GRUB. On Windows, it's the Windows Boot Manager. The bootloader steps up and loads 2 absolute game changers into RAM, the actual operating system kernel and a temporary file system called the initramfs, which holds just enough drivers to recognize your real storage drives.
And the second those pieces are in memory, the baton is officially passed. The bootloader jumps over to the kernel's entry point, and then it just steps aside. It exits the stage. It did its one job, and you won't hear from it again until you reboot.
Which brings us to stage 3. The kernel takes charge.
Now, what's really interesting here is that this is the most critical transition of power in the whole machine. The kernel is the core of your OS, sure, but right at this exact moment, it's waking up to absolute chaos. No real file system, no background processes running, just a bare minimum set of drivers. Kernel initialization is this frantic, high-stakes process of building order out of that chaos, setting up the fundamental machinery that literally every future piece of the OS is going to depend on. So the kernel immediately rolls up its sleeves. It sets up interrupt handling so the hardware can actually signal the CPU, and it gets the CPU scheduler going to decide which programs run when. But the absolute most critical task here, and we really need to highlight this, is how it transitions memory management duties. The kernel takes all that raw, wild, unorganized RAM and locks it down with strict rules. It decides exactly how memory is going to be safely allocated and protected across all the processes that will run later. Without this specific transition, programs would just randomly override each other's data and crash instantly. The kernel totally tames the RAM.
After that, the kernel uses that temporary initramfs we talked about to load the drivers it needs for your actual storage hardware. Once it can talk to your SSD, it mounts the real root file system. This is a massive milestone. We're officially transitioning from a tiny, temporary state sitting in memory to actually accessing your real, fully installed operating system right there on the drive.
All right, stage 4, the power of PID1. With the real file system mounted and the boundaries set, the kernel is finally ready to start its very first user space process, process ID 1. Just think about that number for a second. This isn't just a random background task. This is the absolute prime mover of your system's user space. Every single thing that makes your computer useful to you kicks off right here.
On modern Linux setups, this PID1 process is almost always systemd. Older machines use simpler stuff like sysvinit, but man, the importance of PID1 for managing system services today just cannot be overstated.
Systemd steps up with ultimate authority to start literally everything else your system needs. It spins up the network, so you have Wi-Fi, it fires up the logging, it preps the graphical environments. It is the conductor of the entire operating system's orchestra.
So the crucial point we have to remember is this. Every single other process on the system will eventually be a descendant of this one process. Directly or indirectly, PID1 is the great-great-grandparent of every single app you're going to open today. It's kind of wild to think about.
And this marks a huge architectural shift in control, too. Up until PID 1, the firmware and the kernel were basically running with unrestricted, godlike access to your hardware. But from PID 1 onward, we are firmly in user space. Programs are now forced to run within strict safety boundaries and defined permissions, all policed by those memory management rules the kernel set up just a few seconds ago.
Which takes us to our final stage, the final handoff. We've done a lot of heavy lifting in the dark, but it's finally time to actually put something on the screen. Systemd, our mighty PID1, reaches out and fires up a display manager, say SDDM if you're rocking KDE Plasma. And just like that, all those invisible background processes suddenly manifest visually. The screen lights up, and boom, there's the graphical login screen you're used to seeing.
The second you type your password and hit enter, a full desktop session sparks into existence. Your desktop environment loads, your background apps start syncing, your wallpaper pops up, and that exact moment, that marks the official end of the boot phase. The relay race is over, and you're now interacting with a fully running, fully initialized OS. And this brilliantly illustrates the whole journey we just took. First, the firmware wakes up and tests the hardware. Second, the bootloader grabs the kernel and passes the baton. Third, the kernel tames the memory and mounts the drive. Fourth, the init system, PID1, starts up all the services. And fifth, the display manager finally gives you a UI. It's literally a story of steadily increasing capability, one handoff at a time. That is the entire design philosophy of how a computer boots. Every layer is there simply because the layer before it was too limited to finish the job. Firmware can't manage services. A bootloader can't run a graphical login. It requires absolute, perfect teamwork.
So, I want to leave you with this thought as we wrap up this explainer. The next time you sit down, press that power button and wait those few seconds, will you appreciate the perfect, fragile, highly orchestrated chain reaction happening in the dark? It is this massive digital ballet that happens in the blink of an eye, every single day, right under our noses. Thanks for hanging out with me, and keep wondering about the invisible systems that power our world.